In the last video, we talked about water being amphiprotic. And so this is why it's amphiprotic, because it can act as an acid and a base. And we saw two different examples with two different molecules that water engaged in acid-base chemistry with. Now it turns out that in pure water, right, where we just have water interacting with itself, water also can act as both an acid and a base. So we have some water molecules that are donating a proton, and then we have some water molecules that are receiving it. And we form hydronium ions and hydroxide ions. So this relationship, or this kind of reaction where water is interacting with itself, behaving as both an acid and a base, is called autoionization of water, right? Auto being self. Its equilibrium constant is represented as K sub W, W for water. And our equilibrium constant, right, is equal to the concentration of our products over reactants. In this case, it's just hydronium, the concentration of our hydronium ions times the concentration of our hydroxide ions. And that's all over 1, because water is a liquid. Our reactants are just water, liquid. And the concentration, I'm sorry, not the concentration, the equilibrium constant is equal to 1 times 10 to the minus 14. 1 times 10 to the minus 14. So if we were to calculate the concentration of hydronium ions or hydroxide ions using this equilibrium constant, they are equal. They are equal. So each of them equal 1 times 10 to the minus 7 molarity. So let's talk about pH and pOH, right? And this allows us, these are the measurements. This is how we measure the acidity or basicity of a solution. And it is basically a concentration, or it measures the amount of hydronium ions or protons and hydroxide ions. Now, these concentrations can span many orders of magnitude. So we sort of, you can think of it as like normalizing these values by taking the log of the concentration of hydronium ions and hydroxide ions. So pH is the negative log of our hydronium ion concentration. pOH is the negative log of our hydroxide ion, of our hydroxide ions. So pH and pOH are inversely related to one another. So if we have a high pH, we'd have a low pOH. If we have a high pOH, we'd have a low pH. And we'll come back to that in a little bit. So going back to pure water, where our equilibrium constant is equal to 1 times 10 to the minus 14, from this autoionization reaction, we can establish our pH scale. So when in pure water, when the solution is neutral, so in neutral pure water, our hydronium ions and hydroxide ion concentrations are actually equal to one another. So that means their concentrations are 1 times 10 to the minus 7. And if we take the negative log of that, we'll find that the pH is 7. So this is why pH of 7 indicates that a solution is neutral. Now, if we have a solution where we have more hydronium ions than hydroxide ions, this is an indication that the solution is acidic, right? And this means also that at least at room temperature, the hydronium ion concentration is greater than 1 times 10 to the minus 7. because when it's neutral, that is what its concentration is. So if it's acidic at 25 degrees Celsius, right? This is true for room temperature. Then the solution is acidic, and we have a pH that is less than 7. That is less than 7. At room temperature, if our hydroxide concentration is greater than our hydronium ion concentration, meaning that we have a hydroxide concentration that's greater than 1 times 10 to the minus 7, the solution is basic. And if we take the negative log of that, our pH will always be greater than 7. So this is a table with common acids and bases at room temperature. At room temperature. So this scale that we have of pH 1 to 14 is established at room temperature, right? That scale could slightly shift at a different temperature, right? So this is established at room temperature. Notice that, so we're showing common acids and bases at room temperature, and we're also showing the increasing acid strength and increasing base strength. And we see that as we increase the acid strength, its conjugate base is decreased, is lower. So if we have a strong acid, its conjugate base is weak, right? So there's this inverse relationship between acid and conjugate base strength, or base and its conjugate acid strength. And in this way, pH and pOH are inversely related to each other. So if we have a really, really strong acid, such as perchloric acid, right, which I don't remember what that pH is, but let's just say the pH is 2, right, which is a really strong acid, then the pOH would be, I'm sorry, let me rephrase. If we have a, yes, if we have a strong acid, it would be a lower pH. So if we have a pH of 2, then the pOH would be really high, right? It would actually be 12. It would actually be 12 because pH plus pOH equals 14. So there is this inverse relationship. If we look at a base such as hydroxide ion that is a strong base, we would find that its pH would be low. The pH would be low, but the pOH would be really high because it's a strong base. So the main takeaway is that pH, pOH, which measures acid and base strength, are inversely related to each other.